Okay, so this is the first podcast for Unit 5, which is Thermochemistry and Thermodynamics. It's mostly Chapter 5 and 19 in our book, with a little bit of 8 and 11 sprinkled along. And I indicate for each podcast or for each section where in the book you can find this material. So if you want to read the book to supplement, you can go ahead and do that. Now, I will say that the two biggest issues students have in this unit are going to be both a combination of units, and when I say units, I'm talking about the issue here will be one of whether or not we are dealing with calories or joules or kilojoules, and being clear about what the units in the problem are and what the units being asked for are. We also have to be careful about whether or not the data that you're given is per mole or whether it's per gram. So you want to watch out for those things. In some cases, especially when we get to thermodynamics, you'll get some values that will be in joules and some will be in kilojoules, and you need to add them together, and you need to make sure that you've got them in the same units. In some cases, even the constants have to be changed. So the way you get good at that is by doing the problems along the way. So what I encourage you to do is stop as we get to a problem, try to do the problem, and then watch to see whether or not you got the right answer, or just see if you got the right answer based on the answer in the box, or watch me do it. Okay. But it's important that you do the problems. It's the only way you're going to pick up on common mistakes like that. The other issue is you need to be really careful about being able to identify whether things are going to be a positive value or a negative value. So we'll talk a lot about that. And you've got to get it really clear in your head about when heat is being lost and when heat is being gained. And the same thing with work. So we'll talk about those things. So energy simply, okay. So energy is the ability to do work or produce heat. Okay? Simply, that's the definition. It's the sum of all potential and kinetic energies in a system is known as its internal energy. Okay, so the energy that's possessed in a system is its internal energy. You usually can't measure how much internal energy something has, but you can measure what happens to the change in energy. Okay, so we talked here about potential and kinetic. Potential energy, you will deal a lot with this in physics, but when we're talking about this in terms of chemistry, what we're talking about is the potential energy associated with the bonds, the energy that's in the bonds. Okay, and it has a lot to do with Coulombic attraction. So the reason why reactions occur is because the substance will become more stable if it forms a bond. And by more stable, that means lower potential energy. So bonding, when it produces lower potential energy, is a desirable goal. Okay. So let's take a look at this diagram here, and we can see what's happening when we do some bonding. And actually, let's take a look at this animation first. So if I have two atoms, let's say I've got neon and neon here, and I move this away a little bit. The atoms are attracted slightly, and it's all Coulombic attraction. So the electrons from this atom, in this case neon, is attracted to the nucleus of an adjacent neon atom, right? And they want to be where the potential energy is the lowest. So there's not much difference in energy when they come close together. Now, they don't actually bond. Let's see what happens when we have something that... And let's take a look at the component forces of what we got going on here. So there's some attraction of the electrons to the other nucleus, but there is also repulsion, and that repulsion comes from this nucleus and this nucleus repelling each other. Okay? But if I have something like oxygen, let's turn off the forces for a second, and I have this, here I'm looking at potential energy up here, and it's got some potential energy, and there's a little bit, let's look at the forces now, there's a little bit of attraction towards this. And when it gets close, that's when you have the bond form, because there's a tremendous attraction, Coulombic attraction, and you get this big dip in potential energy. And this vibration is meant to show this is where energy gets released. Energy is being sent out. So there is some repulsive force, the pink, but there's a much greater attractive force between the nuclei. And that's what causes, let me turn those off because it can make you dizzy. That's what causes this bond to form. Okay? So if we go back and look at something like argon and argon, there is some attractive force, okay, but there's an equal repulsive force which keeps them from forming an actual bond, okay? As much as it gets attracted, it gets repelled. Okay, so that's what we're looking at here. We're looking at the distance between the atoms right here, and depending on how close the atoms are, in this case we're talking about hydrogen, will determine whether or not there's a strong or a weak repulsive force. So you can see as the atoms or the nuclei get closer together, there's an increasing attractive force causing a reduction in potential energy to a point where the potential energy is at its absolute bottom, and that's where the bond forms, right? This is why bonds form. They want to reduce energy to become more stable. Now, if these atoms were even closer together, they would start to repel each other. So there's some dip here that is the perfect place for any atom. They're all going to have a shape that looks like this for a bond, right? Where there's this dip in potential energy, and that's where the atom is going to want to exist. So when the atoms bond, the Coulombic attractions between the electrons here and the nuclei here results in energy being released, and it lowers potential energy. So here's the link for the simulation if you want to watch it yourself. By the way, this podcast is going to go through page 1 through 6 in your packet. Okay, so if you want to print those out and get these in color. All right, so if we look at kinetic energy is the energy of motion, and the energy of motion, and that motion can be translational, rotational, and vibrational. Well, what the heck does that mean? So translational means I have a particle that's flying across the page. Rotational means I can have an atom or I've got parts of the atom that can rotate, or part of the molecule that can rotate. And vibrational is just, if I have a solid and it's kind of locked in place, but it's still vibrating. Okay. And as you know, if we draw whooshes on these guys, this is what we'll see if we have a lower temperature, and this is what we'll see if we have a higher temperature. So the kinetic energy is directly proportional to Kelvin temperature. If I double my Kelvin temperature, I am also doubling my kinetic energy. And the formula, as you probably know, for kinetic energy is 1/2 mv squared, where m is mass and v is the velocity, measured in meters per second. Okay. Okay, so if we draw the whooshes, we'll see the longer or the faster speed, more kinetic energy. Okay. All right, so if we took 500 milliliters of water at 25 degrees Celsius and the same amount of water at 35 degrees, then we have less kinetic energy. Okay? So doubling the Kelvin temperature here, results in doubling of the kinetic energy, which also means that we are doubling the velocity. Must be doubling the velocity. I'm really bad with this mouse. I'll get it better as we go. Okay. So here is the diagram you should all be familiar with, the Maxwell-Boltzmann diagram. And what this shows is if I have, so first of all, if I have no energy, I have no particles there, right? But as I add some temperature, the higher the temperature, the higher the kinetic energy, the more spread out this distribution becomes, right? So this distribution, the area under the curve, represents all the particles and how many particles would be at each different energy, right? So if I have a higher energy or a higher temperature, I'm going to have particles that are at all different temperatures, but they're going to be spread out. Okay. So as the Kelvin temperature approaches 0 K, that's the definition of when movement ceases, volume ceases, and it's, remember, a theoretical temperature because particles can't have no motion and they can't have no volume, but it's the lowest possible or just below the lowest possible temperature. Okay. So if I have two systems together, let's say I have a hot cup and a cold cup of water, and I put them close to each other, and I have whooshes here, and we can consider these to be vectors indicating the movement or the direction of the movement, and the lines, like the lines indicating the relative speed, like we did when we draw whooshes. Now this doesn't show any whooshes because it'd be so tiny. So what happens is if I have something that's hot and something that's cold, is the kinetic energy gets transferred from the hot object to the cold object. And that transfer of energy is called heat. That's what heat is. It's the transfer of energy. And that transfer actually occurs through collisions. And it always goes from hot to cold. So you might think you put an ice cube in a hot cup of tea and that you're adding coldness to the tea, but in fact what's happening is those hot particles in the tea are colliding with the particles in the ice and transferring that heat or that energy. Okay? So after a while you reach what's called thermal equilibrium here, where both systems have the same energy. Okay? So the transfer of energy is called heat or heat transfer. It's not a substance, but it's something kind of like money, right? So it doesn't matter whether I have $100 in the bank account or $100 in a check or $100 in cash. It all has some value, even if it might not be something I can hold in my hand. Okay. So important to note that heat is transferred by particle collisions. So let's take a look at a problem. Here's the equation for kinetic energy, and the equation is 1/2 mv squared. Now it's really important that you know that this uses all SI units, and in that case the mass is going to be in kilograms. So this would be a common thing people get wrong, is because they'll develop the kinetic energy answer and use grams, and velocity standard is in meters per second. Okay. Now, it turns out the SI unit for energy is the joule, and the joule is kilograms times meters squared over seconds squared, which is what you get if you multiply kilograms times the square of meters over seconds. Okay, so let's take a look at this problem here. Alright, so we want to know what is the kinetic energy of an argon atom moving at 650 meters per second. Okay, and it tells me the 1 AMU is what the mass of 1 AMU is, so I can use that in my work. Okay, so let's take a look. So I first have to, if I'm going to use the equation KE equals 1/2 mv squared, I first have to get my mass for my argon atom. Okay, so what I know is I have one argon atom, right? I'm just going to call it one argon atom. And I know that one argon atom, from the periodic table, I know that it has 39.98 AMUs, right? And I also know from what's given to me here is that 1 AMU is 1.66 times 10 to the 24th grams. But I need to get this in kilograms, right? Because I got to get kilograms here. So I know that 1,000 grams, whoops, that's 1,000, not 100, is 1 kilogram. And if I multiply that out, I will get 6.631 times 10 to the 26 kilograms. Okay. So now I can plug everything into my equation, which is going to be kinetic energy is 1/2 times mass times volume squared. So 1/2 is 0.5. My mass is 6.631. And I just keep that extra sig fig for doing this. And I figure out my sig figs at the end. That many kilograms times my velocity, which is, tells me up top in the problem, 650 meters per second, and all of that gets squared. Alright, if I multiply 0.5, and you want to do this yourself, make sure you can punch things the right way, times 650 times the mass here, 6.691, I get 1 point, let me see, I've got 2 sig figs here, so I'm going to go with 2 sig figs, 1.4 times 10 to the 20th. Now my units here are going to be kilograms times, based on the velocity, meter squared over second squared. But that is what a joule is, so that is the same as 1.4 times 10 to the 20th joules. Okay. Alright, you find in the next section of your book the discussion of the first law of thermodynamics. So the first law of thermodynamics is what you already know, which is that energy is never created or destroyed. It is just transferred. Okay? And it also means that the energy of the universe is constant. Because in order for a system to gain energy, something else has to lose energy. Okay? And this is where we start to think about what's happening with the direction. Okay. Now, energy is defined, it's often defined as the ability to do work. Okay? And there are two components to energy. There's Q, which is heat, symbol for heat, and there is W for work. So the total energy of a system is the combination of its heat and its work. Alright, so we're going to do some problems looking at what's happening with heat and work. But in order to be able to identify whether Q and W are positive or negative, and this is, again, an area where students often make mistakes, we have to be able to get clear about systems versus surroundings. So if I have a system, let's say a beaker where a reaction is occurring, everything outside of that beaker is considered my surroundings, right? So if that reaction creates energy, that energy is going to leave the system or the beaker where the reaction is occurring and go into the surroundings, which would be the room or the area around the reaction. If I have my hand on my beaker, my hand is part of that surroundings. Okay. So that's system versus surroundings. So let's talk about heat first. And students will often get confused about exothermic versus endothermic. So if something is absorbing heat, it is endothermic, right? Which means it is adding heat, or plus Q. If it is losing heat, it is exothermic. In the area where students get confused, let's say I have this system where I have this beaker, or I have this substance in this beaker, right? And it gets cold. Okay? What's happening here, if it's getting colder, is the system is gaining heat. Now, some students will get confused and say, well, if it's gaining heat, shouldn't this be warmer? And the answer is no. So if I think about putting my hand on, if I think about putting my hand on that beaker, my hand feels cold. And that is because the heat is leaving my hand and going into the beaker. Okay. As opposed to where Q is negative, or a system is exothermic, this is going to be because I have this system. Let's say I have some reaction going on, a combustion reaction or something like that, that generates a lot of heat. The heat that's generated in this reaction is leaving the system. So if I put my hand on that system, that heat leaves the beaker and goes onto my hand, and I say, ouch, because it hurts. Okay. So get really clear in your head about when heat is positive and when heat is negative. When the transfer of heat, if something is getting colder, it is gaining heat. Okay. The other element of the internal energy is work. And you'll do a lot. If you're taking physics now, you've probably done a lot with work already. But when we're talking about chemistry, the work we're talking about is the work associated with gases, and it's a function of pressure. Okay, so gases, as you know, if you're creating more gas, you're creating more pressure, or you're creating more volume. So when we're talking about work relative to gases, we call it PV work. Okay, and work is equal to the negative of the pressure times the change in volume from the gas. Okay, so we have to get clear again about what's happening with work and whether the work is positive or negative. So here I have a system, okay, and there's a reaction taking place, and I have a piston that is movable, right? And so what happens in this reaction is the volume goes down, and as it goes down, the plunger comes down. And because the plunger is coming down, the work is being done on the system. It is compressing it, and because it is compressing it, that is a positive work. Okay, so if I had if I started here, and this was V1 and this is V2, and I cause more gas to be formed, then it's going to push the piston up, and then I have my system doing work on the surroundings. You can think about the piston as the surroundings. It's doing work on the piston, and that would be negative work. The system is losing work to the outside. Okay, so if we have compression of a system because the amount of gas is going down, then we are doing positive work. If we have expansion, if we are creating more gas or creating more volume, then we are doing negative work. The work is leaving the gas and going into the surroundings. Alright, so this looks like a really simple problem, and it is as long as you're clear about positive and negative. So here we want to calculate the energy for a system undergoing an endothermic process. So that tells me that I have a positive Q. Endothermic means heat is going in, so it's a positive Q. Okay, so, and it gives me how much Q, tells me the energy of that, tells me it's heat flow, and that's Q. And it says where 1.4 kilojoules of work is done on the system. On the system means plus W, so something's going to get compressed. Okay. So what I know is the total change in energy is equal to Q plus W. And Q is positive, and in this case W is positive, so I'm simply going to add these together. 15.6 kilojoules plus 1.4 kilojoules is going to give me 17.0 kilojoules. Or just, it should be 17 kilojoules because I only have two sig figs here. Okay. Let's do another one. We want to calculate the work associated with the expansion of a gas from 46 liters to 64 liters at a constant internal pressure of 15 atmospheres. I think it's always a good idea to think about what direction your work is going to be. We're calculating work, and the work associated with the expansion of a gas. So if the gas is expanding, it's pushing out of the cylinder onto the piston, and it's going to be negative work. Okay. So what we saw just a minute ago was work is equal to minus P delta V. Minus the pressure times the change in volume. Okay. Minus the pressure is minus 15 atm times the change in pressure, and it's going to be, change in volume, so it's going to be volume final minus volume initial. So it's going to be 64 liters minus 46 liters. And if I calculate this, the answer will be, and looks like I want 2 sig figs. It's going to be negative 270, and my units are going to be liters here, atmospheres here, so it's going to be liters, atmospheres. Now, you look at that and say, well, that was really easy, but I will tell you, many students will get the sign wrong. You got to be clear on the sign. Okay. Alright, so here's a combination problem. A balloon is being inflated to its full extent by heating the air inside it. If I'm heating the air inside it, let's get really clear. This is plus Q. I'm adding heat, right? In the final stage of this process, the volume of the balloon changes from 4 times 10 to the minus 6 liters to 4.5 times 10 to the minus 6. So this is expansion work. The balloon is pushing out, so this is going to be minus W. Okay? And it tells me how much heat, and it tells me the pressure. Okay, so remember, the change in energy is equal to Q plus my work, and Q work is minus pressure times change in volume. Alright, so let's put them all in. So I have 1.3 times 10 to the 8th joules of of heat, plus my minus P minus 1.0 atm times my change in V. And it looks like I'm going from 4 to 4.5 times 10 to the minus 6. So I'm just going to call this 0.5 times 10 to the minus 6 liters. Okay? So if I multiply 1 times 0.5 times 10 to the minus 6 and add to that 1.3 times 10 to the 8th joules, I end up with a problem, because this is joules and this is going to come out to be liters atmosphere. And the nice thing is it tells you to convert from liters atmospheres to joules. We're going to use this conversion process. Alright? So I'm going to go ahead and just add that here. Let me just erase what I have right here. Alright. So, what I know is 1 liter atmosphere, based on what they told me above, is 101.3 joules. Okay? So I'm going to take 1 times 0.5 times 10 to the minus 6, multiply that times 101.35 to get that in joules. So now I can add this in joules to this in joules, and I end up with 7.9 times 10 to the 7th joules. And that's because I got, let me see, sig figs, I got 2 here, and I've got 3 here, so I should have 2. Okay. Alright, so for the combustion of ethane, ethane is a gas, is work done on the system, by the system, or not at all. Okay. So what we have to do here is figure out what's happening when I combust ethane. So I have this gas ethane. Combustion means I'm going to add oxygen, and I'm going to generate carbon dioxide and water. So I have to figure out what's happening with the volume of gases. These are all gases, right? And if they're gases, I got to figure out whether I have more gas at the end or less gas at the end, so I can know whether or not the work is going to be expansion or compression. Okay, so in order to do this, I got to first balance the equation. So let me see, I've got 6 H's. That's going to make that, I'm going to need to end up doubling this. So make sure you can balance. That's going to be 4. This is going to be, let me see, 6. And that'll be 8 plus 6 is 14, so that becomes 7. Okay. So when I do that, just looking at the coefficients, I have 7 moles of gas here, and I'm going to 4 plus 6 or 10. Whoops, let me see. Whoops. 9 moles of gas here, and I end up with 10 moles of gas here. So if you imagine this happening in a container that has a piston, you know, I have my reaction, and what happens is I create more gas. It pushes the piston up, and by doing that, this system is doing work on the surroundings. So this is going to be minus work, or by the system onto the surroundings. Okay, so there is an assignment in Quest, Thermochem 1, and then there are some book problems. A lot of those are conceptual.